I'll take a rigid body of mass m and radius r. I'll apply force. I'll start pulling it. I'll start dragging it, and this is a rough surface. Then how to calculate the acceleration of center of mass and also the rolling friction. At the moment you start dragging it, what will happen to center of mass? The center of mass is going to accelerate. Let's write all the equation. What can happen? I think it starts rolling. No, it starts rolling. What it makes to roll? We have to generate a set of equations. What makes it to roll? I think the diagrams have become a little bit big. You have question everything in front of you. Let's proceed with the calculations part. There's a point P. So the moment you apply force, center of mass will accelerate. Then if AC the acceleration of center of mass due to translated motion, all points should also have acceleration of center of mass. Then what is the point of contact? Will slip forward, will move forward, and because of this there will be a friction, and there will be a friction. The friction will oppose relative motion, so it will act here. This friction acting, what it does, it will set up a torque, and it will produce angular acceleration. Because of alpha c, there will be a no r alpha c also will come. Then if I go and check it at any instant for no slipping, acceleration of point P along x-axis will be 0. Then AC minus R alpha C will be 0. This is a condition for no slipping. We are discussing now accelerated pure rolling. From why that AC will come? Because I'll apply force F. The center of mass starts describing translative motion. Because the force is acting at center of mass, so only translative motion is try to describe. So since due to translative motion, all points should also have acceleration of center of mass. So the point P, the point of contact, will have acceleration AC like this. Then at the point P is having acceleration towards it, the friction should oppose relative motion. So the friction by the ground on the rigid body will be towards left. This friction will set up a torque, and it set up angular acceleration. Because of angular acceleration, there will be tangential acceleration, that is R alpha C. Then for no slipping, acceleration of point P along x-axis must be 0. This is a condition with that. Then what are the equations? F minus AC. The net resultant force acting on the solid sphere, capital F minus small f, is equal to MAC. Then torque setup about center of mass, IC alpha C. So what is F equal, what is IC? Let me keep as it. For pure rolling, this is AC by R. So F equal to IC AC by R square. Let me substitute this F here. Small f, capital F, please be careful. So this is equation 1, equation 2, and this is equation 3. Solving 1, 2, 3, we'll get expression for friction. This friction I'll substitute in the equation 1. Then we'll get it. IC AC RC square equal to MAC. What is AC? Acceleration of center of mass, FR square by IC plus MR square. Now what is the expression for the friction? This value of AC, let me substitute here. Then the expression for friction will be F is equal to IC RC square FR square by IC plus MR square. R square get cancelled. So F by 1 plus mr square by IC. This is the one, you put it like this. Okay, now look at now something I brought very interesting here. Now, what is the rigid body? We'll see. And what is this? I'll call strictly rolling friction. Not sliding friction. So what do you mean by rolling friction? As there's a new type of friction I'm introducing here called as rolling friction. Means now, so like let's do one thing. I'll increase applied force. MRIC, they will not change, no? I think by applied force, as you increase applied force, these quantities will not change. Then what should vary? The friction is going to vary, the rolling friction. Okay, sir, then it must be a static friction. Why you are not calling static? That's all, no? So let's go back to the definition. You keep a body on a rough surface, and as you increase applied force, the friction will also increase. Then that friction will call static, no? So as you increase applied force, the friction force acting. So they should be static. But you know, is it body static? Center of mass is having displacement. It is having motion, no? It will accelerate. It will get undergo displacement. Then what is the velocity of center of mass at any instant of time? We can use all formula. What is the acceleration, displacement of center of mass at any time? Don't think that it will be there only. It will move. You do one thing, just push any your vehicle, two-wheeler, or if you have any tire, or you go to the kitchen, some any container, steel container, try to push it. So you are only pushing that one. Say, what is this F? Push force, no? Or if you want, you can call pull force. So if you are saying push means you have to show it here, F. Then as you're pushing it, what it should slide, no? But it starts rolling. Why did it roll? Because of the friction. That you can do on what? On the carpet or on the bed. You put any cylindrical container which is there in the kitchen, just bring it and try to push it, no? It starts rotating. What makes it to rotate? The friction. And this friction is what now? Rolling friction I'll call, because as I increase applied force, this is increasing. But sir, but you should call static. Okay, let's come for here. This particular friction depends also on the distribution of mass. What is IC? Moment of inertia, distribution of mass. But we know static friction is independent of distribution of mass, shape of the body. Am I right? In the friction chapter, we never bothered about the shape of the body. Here what happened? The shape of the body also matters a lot. So therefore, this is a rolling friction. Then what is the maximum permitted value of rolling friction? Mu s mg. Mu s mg. So therefore, is it a kinetic? No. Is it a static? No. So a new category of friction, we'll call this as rolling friction, which depends on applied force and also distribution of mass. Then you just see, like, this problem will become very beautiful if you draw a tabular column. So when you draw a tabular column, let me show. So there's a body, rigid body, acceleration of center, moment of inertia, acceleration of center of mass, and the friction. Let me start with a ring or hollow cylinder. Both are same. Disc or that one, solid cylinder is same. Let me go for solid sphere. All are having same mass. So mr square by 2, 2 by 5 mr square. Okay, let's calculate acceleration. What should be the acceleration of this one? High C is what? Mr square. So how much will get acceleration? F by 2m. Then how much of friction will be? F by 2. If it were static, it would have been equal to F, no? Then let it be disk. Let it be a disk. If it's a disk, how much will be? Mr square by 2. So 2F by 3m. Then mr square by 2, F by 3. I think the tabular column speaks a lot. All three rigid bodies, they're having same mass and same radius r. Means it is like this. I think you're still not understanding. This is a ring. Next, what we have? A disk. Next, what we have is a solid sphere. And according to this concept, what is telling? Everything is oh, I put it for all the rigid bodies, the force, the push or pull force is applied like this. Please do understand, this is something very fundamental. I'm using word fundamental. All are having same mass. Now, what do we expect friction? Here, the friction is how much? F by 2. Here, the friction is how much? F by 3. Anybody acceleration? How much this will be? Okay, I want friction only. 2 by 5 mr square, no? So 2 by 5. I think 2f by 7, the friction. You see the friction acting here. Yes. I'll come to that one. Yes, the rolling friction and the normal reaction. The net work done by rolling friction is 0, but they will do work. The friction does work. Rolling friction does work. Net work done by friction will be 0 in pure rolling. Look at now. Definitely, I think this is not static friction. All rigid bodies are having same mass. Same force is applied at the center of mass. At center of mass only the force is applied. But what we are getting, the rolling friction acting is different. So this shows that it's not like a static. Sir, why can't you call kinetic? Because it's moving. Why can't you call kinetic friction? Depends on what? Depends on normal contact. It is independent of normal contact. So therefore, it is not a static, nor a kinetic. What it is, it's just a rolling friction. This is very important, and we don't have quotient of rolling friction. It's a wrong thing. Sir, thank you very much for introducing one more friction, mu r. What is mu r? Quotient of rolling friction. I think no book in the world has defined except our books. Some of our books from NEET books, I don't know, some NEET teacher has introduced this mu r, and some are practicing it. This is stupidity. If you surprisingly, last year question came in mains in our weekend exams. 5f by 7, 2 by 5. Okay, 5f by 7. Yeah. Luckily that one, so this particular question came, I think it's a wrong idea. Please do follow. There's nothing called like a mu r, no book has defined. Mu s and mu k are there. This is not there, totally. So this is a rolling friction is what it is. So rolling friction depends on what? Applied force and also distribution of mass. I think we have everything in front of you very clearly. I gave tabular column. So rolling friction depends on what? Depends on applied force and we never said like this, no? Distribution of mass. Distribution of mass means nothing but what? Shape of the object. Okay, tomorrow I'll focus on the work done. How the work done by this, it will come that one. Okay, try to revise all. Tomorrow we can focus on the numericals part. I think I took a lot of 5 minutes extra time. Okay, we'll wind up the class. Okay, thank you all of you.
Thank you, sir.